Now the other thing they ask us about is the secant line, and make an approximation for that. Now remember, the secant line works by the same rules the tangent line does, as long as the point is outside the domain where the line is intersecting the graph. So for instance, we have a concave down situation. We have x values at 5 and 8, and if we have a secant line, sure, we'll get an overestimate if we're outside the window, but they're asking us specifically about f of 7, which is inside the window. So we should get, for the secant line, a low estimate in this case. So I'm just going to make a note, since 7, since 7 is between 5 and 8, and f double prime of 7 is negative, the secant line approximation will be less than f of 7. So they're saying the secant line approximation, this point, will be less than the actual value of f of 7. That would be a slight bit higher. Oops, I should make this so it's on the screen. There. So then we got to get the actual secant line approximation. We need a slope, so between 5 and 8, slope is rise over run. Our rise, we can see we're rising 5 units from -2 to +3, and we're running 3 units from 5 to 8. For x and y, I can use either of these ordered pairs. I'll use this. So I have -2 for y. M becomes 5/3. X becomes 5 plus b. This is 25/3. If I take that away, -2 is like 6/3. So I'd get -31/3 for b. So my equation would be y equals slope is 5/3, and then -31/3 for b. If I plug 7 in, I'd get 35/3 minus 31/3 would give me 4/3. That's the target number that they gave us in the problem. We've already established that this will be less than f of 7. So I'm just going to make it official at the bottom. In this last example, which is also an old AP problem, they give us a table of water in a tub, the temperatures of water in a tub over a given time. It's a strictly increasing, twice differentiable function. The water is being heated for 30 minutes, starting at time t equals 0. And they give us 20 minutes worth of random values. Then they give us a function. Obviously the average temperature in the water is given by this function. What's the 1/20th? Well, average value, I like to call integral over interval. That's exactly what this is. They're taking the integral of w on that interval, and I always put it over 20, so it's over interval. Books and texts typically, as a standard, we'll just call it 1 over the interval, but that doesn't have the same ring to it. But it's the same thing. It says to use a left Riemann sum with 4 subintervals that you'd predict using in the data to approximate that value. So let's start with that. I'm going to have 1, 2, 3, 4 rectangles. My first rectangle is going to, I'm going to keep that 1/20th. My first rectangle is going to be 4 units wide, and it's going to have a left endpoint height of 55. That's what they mean by a left Riemann sum. My second rectangle is going to have a width of 5, and we're going to use the height 57.1. My next rectangle is going to have a height of 6, and we're going to use 61.8 for the height. And my final rectangle is going to have a height of 5, and we're going to use 67.9 for the height. This is a good calculator problem. But if you crunch all the numbers, you get 60.79, which is a fairly reasonable number when you compare it to what is actually in the table for those y values. It seems right in line with that. Then it says, does this approximation, I should label this too probably, this would be in degrees Fahrenheit. Does this approximation an overestimate or an underestimate of the average temperature? Now they are telling us, there it is, they are telling us that this is a strictly increasing function, so I'm going to say, so since w is increasing, w prime has to be positive for all t, which means that our approximation is going to actually be less than the actual value that we would get if we knew the actual numbers. So that's the idea. We're dealing with overestimates and underestimates with tangent lines and overestimates and underestimates with area under a curve.